All right, welcome back again, everybody. Today we're doing section 2.4. This section is all about important attributes of functions, basically just some properties that functions may exhibit that we want to be able to look for, identify, define, etc. Let me pull up the slides and we will get started. Here we go. We're going to start the section off by talking about what are called even and odd functions. Oops, let me pull out my laser pointer here. Even and odd functions. Then we're going to talk about intervals of increase and decrease. These are basically places where the function is increasing in value or where it's decreasing in value or even not changing in value. That's what we call a constant function or constant on an interval. Then we're going to talk about absolute or global maximum and minimum values. You can think of these as just the greatest and smallest value that the function can achieve. Then we're going to talk about local minima and maxima. It's kind of the same idea, except localized to small intervals. Then we're going to finish up by talking about the extreme value theorem, which is a really important theorem when certain properties of a function are satisfied. You get this really powerful conclusion. Right, so let's start with what an even function is. We say that a function f is even if and only if f of negative x equals f of x for every input x. So what this really means is that if you change the sign of an input, it does not change the sign of the output. So if you replace x with negative x, that doesn't matter. You're still going to get the same output value, okay? That's what it means. Now, graphically, these functions have a symmetry, and they're symmetric about the y-axis where x is equal to 0. So you can, if you can see the graph of a function, you can tell immediately if it is even or not. Let's take a look right now. So here I've got two graphs. This is the graph of the function x squared minus 2. And what I want to draw your attention to is this horizontal symmetry it has with the y-axis. So let me draw a vertical line right here. There, that's pretty good. That's pretty good. Right. Okay, so notice that on this graph, this side of the graph looks the same as this side of the graph. So it's basically like this side of the graph is a reflection of this side. That's exactly what it means to be an even function. You've got that horizontal symmetry. Because remember, all the x values over here are negative, and all the x values over here are positive, right? So what that's saying is, hey, it doesn't matter if you plug in the negative or the positive value, the height is going to be the same. This is why, like, if you plug in -2, or maybe I'll say, yeah, if you plug in -2, you're going to get 2. And if you plug in 2, you're going to get 2. So there's that horizontal symmetry. Over here, this is a graph of the cosine function, and it exhibits that same symmetry. So let me move this line over here. There we go. And here again, if you look, this side of the graph looks the same as this side of the graph. So you've got that horizontal symmetry again, right? Okay, now let's compare that to an odd function. So a function f is odd if and only if f of negative x equals negative f of x. So what this means is if you change the sign of the input, it changes the sign of the output, and that's for every single input x. Basically, if you take x and you make it negative instead, or you make it opposite instead, then you're going to get the opposite of that associated output value, right? That's what it means. Now, these functions also exhibit a symmetry, but it's different than an even function. These functions exhibit symmetry about the origin. So it's like they're reflected through the origin. Or another way of thinking about it is you've got like a double reflection, a horizontal and a vertical reflection. Let's take a look. So here, I've got the graph of x cubed minus 2x. And I'm going to emphasize the origin here for a sec. There we go. And what I want you to notice is that this part of the graph here looks the same as this part of the graph, except it's been almost like doubly reflected, right? It's basically you're reflecting through the origin, just like this, like so. That's what's happening. Another way of thinking about it is you can almost think about it as reflecting upward and then reflecting across, and that will give you the same thing. Or maybe even think about it as like rotating this like so, and you'll get that same piece of the graph. That's symmetry through the origin. Here, this is the graph of the sine function, and it exhibits that same symmetry, right? So here's the origin. And it's the same kind of thing. If you look at like this point, it gets reflected to this point here. through the origin. And that works for any one of these points, right? There's the symmetry. Or again, you could almost think about taking this and rotating it like that, and then it'll line up with this one. So that's an odd function. Right. Now let's go to our first example problem, and I do want you to try this one on your own. So I want you to try determining whether the function 5x cubed minus x is even, odd, or neither, and then use a graphing utility to verify it, maybe something like Desmos, all right? Before you start, one thing I do want to point out, graphs or functions, graphs of functions may not be even or odd. It's not like every function is even or odd. You can have functions that are neither even nor odd. So evenness and oddness is actually a pretty special property to have. It's going to be really critical when you get into Calc 1 and Calc 2, because if you can recognize that a function is even or odd, then it can save you a lot of work if you're integrating that function over a symmetric interval. All right? You'll talk more about that next semester. But this one, I want you to think about it for a second, right? And then I want you to say something out loud. Remember, you don't have to say it to anybody. If you're watching this on your own, that's fine. Just talk to yourself. Trust me, you're not weird. It will help your brain make sense of things. So say something out loud about maybe how you would start this problem. Okay, and now try to work it out on your own, and we will do it together in a moment. Okay, here we go. So, how are we going to do this? Well, if we're going to determine if the function is even or odd, we have to use the definition of even or oddness. So, remember what you do when you want to see if a function is even or odd, you change the sign of the input and see what output you get. So, what I'm going to do is replace every instance of x in this function with the opposite of x, and we're just going to massage things a bit to see what we get. So, I replace x with negative x, right? Negative x cubed is just going to be negative x. So this term becomes this. And then negative negative x is positive x. And now pause here for just a second. I'm going to do something clever, and we're going to see this technique show up a lot. You'll see it in, frankly, like every math class. Here, I'm going to factor a -1 out of both of these terms. So I'm going to factor a -1 out of this, and I'm going to factor a -1 out of this. And when I do that, I get negative 5x cubed minus x. And now here's the important thing to recognize. This 5x cubed minus x is equal to h of x, literally equal to h of x. It's the output of the function h, right? So now we literally have the opposite of h of x. So we've shown through this string of true equalities, this chain of true equalities, which you want to try to emulate with your own work, that h of negative x equals negative h of x. So that means h has to be odd by definition, odd by definition. So this is how you show it algebraically, right? What does it look like geometrically? This is where the graphing utility comes in. So if we take a look at the graph on Desmos or a graphing calculator or any other graphing utility you want to use, you'll see that it has that symmetry about the origin. Here it is, right? Oops, there you go. So like this piece here looks the same as this piece right here. So it's symmetric about the origin. Now we've visually verified that it is actually an odd function. All right, so next property we want to take a look at is intervals of increase or decrease. So we're about to get a whole bunch of definitions. So, take a deep breath for a minute. Okay, we're about to get a whole bunch of definitions. The good news about these definitions is they match your intuition. So this is a rigorous way of, I should just say, this is a meaningful way of assigning rigorousness to your intuition. Because when you start getting into the weeds and digging into the details of things, you need those rigorous definitions to be able to speak logically and rationally. So when you hear things like the function is increasing, the function is decreasing, it really does mean what you would think. It's increasing if it's going up, it's decreasing if it's going down, and it's constant if it's just staying at the same level. All right, but we're going to go through all the technical definitions. So a function f is constant on some interval I if the output f of x1 equals the output f of x2 for every 2 points x1 and x2 in that interval I. All right. And this is a picture of what it looks like. This is what a constant function looks like. Here's the value x1, x2. Here's the point x1 comma f of x1, x2 comma f of x2, and you'll notice that the height is the same for these. So in other words, the outputs are the same value. This is what a constant function looks like. Straight line. This is actually one of those important graphs you're supposed to memorize, right? Constant functions. F of x equals b, and we changed b to be a bunch of different numbers. This is what a constant function is. Right now, there's a notion of what's called strictly increasing. So we say this, a function is called strictly increasing on an interval if f of x1 is strictly less than f of x2 whenever x1 is strictly less than x2 in that interval, whatever the interval is, your choice. So again, here's a picture of it. And let me zoom in a little bit. And actually, yeah, this will work for this one. So strictly increasing means what you think. It means your function is going to grow in size, right? Now, the strict part, we're going to talk more about in a minute, but the strict part basically means you can't have any constant parts in that interval. So here's an example of a function that is strictly increasing. It is going up. Here's another example of a function that is strictly increasing. It's going up, right? Now, this curvature that you're noticing, let me zoom out again. The curvature, the difference between these two graphs that you're noticing, that's actually what we call, well, curvature or concavity. And you're going to study that way more when you get into Calc 1, because you're going to figure out how to determine if a function is concave up and concave down. This is what we would call concave up and concave down, all right? Now, compare this definition, strictly increasing, to this one. This is a function that we call non-decreasing or simply increasing. All right, so a function is called non-decreasing or just simply increasing if f of x1 is less than or equal to f of x2 on that interval. All right, so it's the lack of strictness that makes this just simply increasing, right? So let me flash back and forth for a sec. Strictly increasing means this is a strict inequality between the outputs. Increasing or non-decreasing means it's not a strict inequality. And the distinction here is that if your function is increasing, it could actually keep the same value on some subinterval there, all right? This is actually one of the reasons why I kind of prefer the phrase or the term non-decreasing, because usually when you just say increasing, it gets a bit confusing. It's like, wait, increasing or you mean strictly increasing? Well, this function is definitely not decreasing. So that's why non-decreasing is sometimes clearer. This function is maybe not always going up because it stays constant right here, but it is definitely not going down. It is not decreasing. So this is a non-decreasing function, which we sometimes call increasing. All right. Now, let's look at the flip side of all this. Let's do the same thing, but for decreasing functions. So this a function is called strictly decreasing if, oh no, there's a typo right here. Too many typos. If f of x1 is greater than, I'll fix that in the next, after I record this. If f of x1 is greater than, strictly greater than f of x2, whenever x1 is less than x2 in that interval. So here's two examples, right? Zoom in. Okay, here's a function where this is f of x1, and your function is going down. So the height f of x2 is less than, strictly less than f of x1. That's what's happening. So this is a function that is strictly decreasing. Here is another function that is strictly decreasing. It's going down. F of x1 is strictly greater than f of x2. That's the basic idea. All right, so let me zoom out. Okay, and again, let's compare this to non-increasing or decreasing. So we say that a function f is non-increasing if f of x1 is greater than or equal to f of x2. So just like before, there's the possibility that your function could be constant in there somewhere, but on the whole, it's still going down, right? And again, this is why I kind of prefer the term non-increasing. This function is definitely not increasing. It is definitely not increasing, so we say non-increasing, or we just call it decreasing because it's going down, even though it is constant right here. All right? So it still fits your intuition, right? Okay. Now, let's kind of summarize those. So, when your function is strictly increasing or decreasing, we call that strictly monotonic. Monotonic, if you think about the word monotone, right, it means like one tone, literally means one tone etymologically. So, monotonic means it is keeping the same behavior in this context. So, a function is strictly monotonic on an interval if it is either strictly increasing or strictly decreasing, but not both. It can't do both on the interval. And then we just say that a function is monotonic if it is increasing or decreasing, but not both. Right. Okay. Now, uh, yeah, so this is the thing. The distinction between the strict increase and not strict increase, and strict decrease and not strict decrease, it might seem pedantic or persnickety, but it really is not. The distinction becomes critical when we investigate inverse functions because strictly monotonic continuous functions exhibit a really important property that just plain monotonic functions do not exhibit. All right. So that strictness can be very, very important. You're going to see it in a really important way when you get to Calc 1. We're also going to see it again when we talk about logarithms. All right. Um, Now, one other note about this, an arbitrary function, just some random function that you pick out of thin air, it may have any or all of these properties. It could be strictly increasing in places, it could be decreasing in places, it could be constant in places. It can have any of these properties, right? On any given interval. But in practice, we usually want to find the intervals where it has just one of these properties, right? So imagine you've got some crazy, funky function doing all sorts of crazy stuff. A lot of times, what you want to do is say, okay, this function is doing a bunch of crazy stuff, but where is it increasing? Okay, great. Now, where is it decreasing? Okay, great. Now, where is it constant? And you want to break it down into all these pieces and study the pieces separately. That's why we have all of these definitions. All right. So next, let's talk about absolute or global maximum and minimum values. So here it is, and I've got some nice pictures here. So let C be a number in the domain D of a function f, then f of c is the absolute or global maximum of f on its domain if the output f of c is greater than or equal to the output f of x for all x in the domain, right? Let me do this for a second. Just ponder that for a minute. Ponder what I just said for just a moment. I know it's kind of a lot to take in, right? Right. Now let's compare that to the global minimum, right? So this value here is the absolute or global minimum value of f on the domain if f of c is less than or equal to f of x for all x in the domain. So what we are really saying here is literally the highest value that f can achieve and the lowest value that f can achieve. So on this picture here, actually, I'm going to need, I finally got a better zooming here, so let me pull this up for a sec. So I can zoom in a little more. There we go. That's a little bit better. Now I can get a little bit closer. Uh, so take a look at this function f right here for a minute. What we want to know is just what is the highest possible point? The highest possible point, and you can see it quite literally here, right? This is the highest possible point, f of x1. So that's what we call this is the absolute maximum value of f, right? The output where f is the highest, the f of x is the highest, right? Then you can contrast that with the absolute minimum value, which is right occurring right here. It's f of x4 in this case, right? So now we're looking for the absolute lowest point on the graph. The graph can do all sorts of things in between, right? But we're looking for the absolute or the global max and min. That's the basic idea, okay? Right. And let me parse this out a little bit more. Oh, wait, let me go back to this. There we go. Let me parse this out a little bit more. What this definition is saying is basically whatever that value is, it's greater than or equal to all the other output values, right? That makes sense. That's the absolute maximum. It's greater than or equal to every other value. That's absolute max, right? Here, this is saying this is less than or equal to every other value. Got to be the absolute minimum, right? Less than or equal to every other value. That's the minimum, the absolute minimum, right? um, Now, in general, the absolute max and absolute min are called extreme values of f. And here's a really, really important note. We're going to see this. We're going to see this when we talk about the extreme value theorem. The absolute minimum or maximum of a function may not exist. Yeah, functions may not have an absolute maximum value. They may not have an absolute minimum value. So this is a special property that a function can have, right? It's not just that it's always going to happen. You have to have some specific things for this attribute to manifest in a given function, right? So here is kind of the distinction here. Keep in mind that for a function to have a value at a point, it must actually be defined at that point. So maybe just a quick example, maybe a little bit of foreshadowing. If a function just keeps going up and 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 up forever, it's got no absolute maximum, right? If a function keeps going up to infinity at some point, or just it never, just it could be any number of points, right? It's never going to achieve an absolute maximum value. It keeps getting bigger no matter what. Absolute maximum doesn't exist. That's the idea. Okay, now that we've talked about these absolute and global maximum and minimum values, or sorry, absolute slash global maximum and minimum values, let's focus our attention a bit more on local maximum and minimum values. So this is a bit different. Now what we're going to do is we're going to restrict ourselves to subsets of the domain. We're basically going to go put the blinders on, and we're going to look at little pieces of the domain. And when we do that, we can start talking about local maxima and minima, localizing our attention. So throughout this course, there's going to be a discussion about local behavior versus global behavior. And this is why we like to use those terms. Local is isolating your attention. Global means looking at the whole big picture. All right. So, and I got this really cool picture here. The number f of c is a local maximum of f if f of c is greater than or equal to f of x when x is, quote, near the number c. All right, we're going to make sense of that in just a moment here. We're going to define near in just a second. And it's a local minimum if f of c is less than or equal to f of x when x is near c. So this is basically the same definition that we had for absolute, max and min, right? Maximum, minimum. The only difference now is we're localizing our attention to an interval within the domain somewhere. All right. Let me see. Do I want to do this yet? Yeah, okay. So what do I mean by near? Because when I say something like near with quotes, that's not rigorous enough to build a proper definition off of. It can give us some intuition. Near just means you're close, right? So what do we mean more specifically when we say near? We mean on an open interval containing that point, right? And this actually means that the endpoints of that interval are not included. An open interval means parentheses on the endpoints, right? That's an open interval. So when we speak of a point being near, we're talking about putting an open interval around the value x, and we're just going to look on that interval and see what happens. So let me zoom in on this picture. I'm going to zoom in a little more here. Oop, hey, come back, come back. There you are. So I've got some examples here. There we go. So this is the same function we were looking at, right? But now what I'm doing is I'm localizing or isolating my focus. Like, let's look at this interval for a minute. If I look at this interval for a minute and I trace up to the graph, what I see here is that there's this maximum value here on this interval, right? So this point is above all of the other points on that interval. So we can call this a local maximum value. This is a local maximum value, meaning if you isolate your attention to this space, it's going to be bigger than all the other points near it. And then compare that to this one over here. This is a local minimum. Again, we're isolating our attention, localizing our attention. There's this low point in the graph, low point in the graph. And if you look around this point, all the other values are greater than the value at this point. That means it's a local minimum. Now notice here, this is not the global minimum. The global minimum is down here, right? That's the global minimum. This point is lower than all the other points on the entire graph. That's why that word global is used, global or absolute. Here we have another local maximum, same idea. So intuitively, what you're looking for, local maxima are the peaks, they're the tops of the mountains, and then local minima are the troughs, they're the bottom of the mountain pass. That's basically what that is right there. So local maxes, local minima. Um, Now, I hope that makes sense. If it doesn't, we can talk more about it in class. But we do need to discuss a technical note. So let me go back to the slides, this version of the slides. Okay, so there's a technical note that we need to talk about here because this can clear up a lot of problems. And this is consistent with what you will see when you take Calculus 1. So because of the way we've chosen to define local maxima and minima using open intervals, what this means is that endpoints of the domain of a function cannot be local mins or maxes. So this might feel a little bit weird, but what I'm saying is, like in this example, this is not a local min. This is not a local minimum, all right? So the endpoints of the domain of a function cannot be local minima nor local maxima. Might feel weird, but there's a reason for it. So this is kind of a good explanation. I always thought it was kind of weird, so I came up with this explanation, and I think this picture clears it up. Um, let's pretend for a minute that the domain of a function f is the closed interval from a to b. The reason that we can't have a local max occurring or a min occurring at these two endpoints is because if we tried to center an open interval around these points, let's just pick A for a minute, then look here at this diagram, right? So if we try to center an open interval here around A, then we actually can't say that f of x is greater than f of a, nor f of x is less than or equal to f of a when we're near A, because our function is not defined over here. So it feels a bit pedantic, but it is important. Um, yeah, this open interval, it reaches outside the domain of F. So we can't actually verify that this is true for all points in this open interval that we selected. Okay, think about that for just a minute. Let me zoom out and I want you to just kind of ponder this for just a moment here. Okay, and now I want you to try to say this in your own words, and then I'll say it in my own words again. Okay. Yeah, so the basic idea is this. Endpoints of the domain cannot be local maxes or mins. That's the easiest takeaway, all right? Okay, now let's practice a little bit. So these are some questions, and I do want you to try these on your own, and then we'll do them together. So this is a multiple part question. I'm giving you a graph here. This is a graph of some function, y equals f of x. My questions to you are, at what values of x does f have a local maximum? And what is the maximum value at that point? At what values of x does f have a local minimum? And what is the minimum value at that point? Or points, I should say. And then I want you to find the intervals of increase and decrease, okay? So think about this for a second. Okay, and then say something about out loud about maybe how you would start. What do you want to try first? Okay, now work it out on your own and we'll do it together in just a moment. Okay, all right. Okay, so let's start with part A. So at what values of x does f have a local maximum? What you're really looking for are, actually, hold on. Maybe I'm going to use this for a second. Let me go to this one. Yeah, okay. So what you're really looking for when you're looking for local maxima are those little peaks, right? So there's one right here. There's a peak. Oops. There's a peak right here. So what is the x value that corresponds to it? It's 1. And what is the maximum value there? It is 2. There we go. So when we say the word value, like maximum value or minimum value, we mean the output, right? So what I'm saying here is when x is 1, f of x is 2. So that is a local maximum, all right? Now, what about local minima? So there's two local minima on this picture. I hope you can see them, right here and right here. You're looking for the troughs, right? The bottom of the mountain passes. So there's local minima at x equals -2 and x equals 3, right? And then what are the minimum values at those points? You basically just trace over. So here, the local minimum value is -4, and here, the local minimum value is 0. So what I'm saying here is, yeah, local minimum value of -4 at x equals -2, local minimum value of 0 at x equals 3. That's the distinction there. Okay, next, where is it increasing and decreasing? So, couple notes about this one. Um, Remember, increasing and decreasing agrees with your intuition. Increasing means the function is growing in size, and decreasing means it's getting smaller in size, right? It's going down, or I should say value. So the function is decreasing, hey, come here, on this interval and this interval. You see how the values are going down as x goes from left to right, right? So those are the intervals where it is decreasing, -infinity to -2 and 1 to 3. Couple notes, let me add this. These should be x values. So these intervals are in terms of x values, okay? We want to know what are the inputs that give us decreasing values. Then we want to know what are the inputs that give us increasing values. So the function is increasing on these parts of the graph, there and there. So if you look at the intervals, it's -2 to 1 and 3 to 5. And then here it's -infinity to -2 and then 1 to 3, just like that. Now I'm gonna erase there you go. So now we can really see those intervals, right? And maybe I'll even highlight this right here. There we go, increasing on those intervals. So those are in terms of x values. Another important point that I want to make is this, and I'll add this here. When we speak of intervals of increase or decrease, always use parentheses, right? And again, there's a reason for that. It's because it doesn't make sense to include an endpoint when you're talking about an interval of increase or decrease, because kind of, if you look at the definition, at this point, the function is neither increasing or decreasing, but that's because it doesn't even make sense to talk about increasing or decreasing at a point. You must have an interval in order to talk about increase or decrease, right? You can't say if something is getting larger if you're only at a point. So we tend to omit the endpoints whenever we talk about increase or decrease, those intervals, all right? Okay, now let me give you another problem to try. Next, here's another graph, and what I want you to do is I want you to find the extreme values of the function f pictured, meaning the global maxima and minima, if they exist. And then I want you to find any local minima or maxima. Okay, so think about this one. Right? Say something out loud to yourself or to your friend or to your dog or to your cat about what you might try. Maybe remind yourself of the definition of these things, right? And then try to work it out on your own, and we will do it together in a moment. All right, here we go. Let me zoom in on this graph a little bit here. Need to zoom in a tiny bit. Um, Okay, so we're trying to find everything, local and global mins and maxes. And we got to be a little bit careful here. So one thing I notice is this. Notice that the graph goes on forever. that means that the function values are going to get larger and larger without bound. So that means that there is absolute maximum, no absolute maximum whatsoever. Then it appears that the graph, well, at first glance, it seems like it's achieving a minimum value, right? Like it's not getting any lower than this. But then if you look closely, open circle, that point is not included in the graph. So that means that this function is not achieving an absolute minimum value at all, right? Remember what I said earlier in this lecture, in order for a function to have a value at a point, it has to actually be defined at that point. And here, the function is not defined there. So this function doesn't achieve an absolute minimum either. So here is a function, here's an example where it doesn't have an absolute max and it doesn't have an absolute minimum, right? No absolute max and no absolute minimum. I think I say that right here. Yeah, exactly. Okay, now what about local maxes and mins? Let's take another look here. Well, I only see one potential low point. That's like right here, but that's not in the domain of the function, so there is no local minimum. This function has no local minimum. All right, now what about this right here? Ooh, okay, what is this? Could that be a local maximum? Hmm, that endpoint, could that be a local maximum? The answer is no, it cannot, right? That cannot be. There's no local minimum and there's no local maximum. So this is kind of a funny example because the answer is no to all of the questions. Remember, the reason that this is not considered a local maximum value is because if I put an open interval, maybe I'll use, oh, it doesn't matter. Okay. If I put an open interval around the number 3, the function's defined here. The function is defined here, but the function is not defined here, right? So I can't talk about those values applying to the function. So this is a graph of a function that has no absolute maximum value, no absolute minimum value, no local minimums anywhere, and no local maximums anywhere. None of them. Interesting stuff, huh? That's also why we need those definitions to make sense of these things. Okay, so now let's answer maybe a bigger question, maybe just a more straightforward question. How do you actually find the absolute maxima and minima of a continuous function on some closed interval? Like, what is the process? So here is the step-by-step process. This is what you do. If someone says, hey, find the absolute maxima and minima. First, you find the values of f at all the local minima and maxima. So you've got to analyze the function in its domain first and find all those peaks and all those troughs. Then you're going to find the values of f at the endpoints, a and b. Literally just plug those numbers into the function and see what you get. Then the largest and the smallest of these values are the absolute max and the absolute min, respectively. So that's how you find the absolute max and mins. Okay? Check all inside, test the endpoints, and then pick the biggest and pick the smallest. That's all you got to do. Right. Now, this kind of wraps things up, leading us to something called the extreme value theorem. Since we're talking about extreme values, absolute maxes, mins, for that, we need a definition of continuity. This is a more intuitive definition of continuity. This is kind of the definition that you normally get in a pre-calculus class. You will make this definition rigorous when you get to Calc 1. It may seem rigorous, but it's not. This is not rigorous enough to define continuity of a function. But it's a good intuition and it agrees with exactly what you would think. So a function f is continuous if its graph has no gaps or holes. So intuitively, you could draw a continuous function without lifting the pen from the paper. Easy example, here we go. That's a continuous function. That's a continuous function. That's a continuous function. When is it not continuous? If you've got gaps, discontinuous, or if you've got holes, discontinuous, right? Discontinuous, discontinuous, discontinuous. So that's what we mean by continuous and not continuous, right? So just take that as the definition for now. You'll make that more rigorous in Calc 1. This is about all we need to make sense of things in this class. Now that we have that, we can finally give and state the extreme value theorem. So here it is. If f is a continuous function defined on a closed interval, a to b, then f must achieve an absolute maximum value and it must achieve an absolute minimum value on that interval. Okay? So here's one that I really do want you to ponder for a second. So think about this for a sec. Just stare at it, read it over in your head once or twice. Okay. And now say it out loud. Read it out loud to yourself. Read it out loud to your friend, your parents, your sisters, your brothers, your dogs, your cats. Just read it out loud, even to yourself. Okay. Now, let's talk a little bit more about this because this is actually a pretty powerful result. Wait, did I say this here? Yeah, yeah, okay, I do see it right here. So, uh, since you've made sense of it and read it over a couple times, it seems plausible, but it is actually a very powerful result. It's just saying if your function's continuous on a closed interval, then you're guaranteed to have a maximum value, and you're guaranteed to have a minimum value, an absolute minimum value. That's pretty wild. I mean, all you need is continuity and a closed interval, and you're guaranteed to get an absolute max and min. Guaranteed. All right. Um, we cannot prove this, unfortunately. The proof is a little bit analytical, but those of you that are math majors, you will definitely see it in a analysis course, your first like undergraduate real analysis course. You'll prove it. You'll probably have to prove it on a test, if I'm being honest. Uh, the other note I want to give here is that the extreme values, the absolute maxes and the absolute mins, they can be achieved in more than one place. So I've got a couple examples here. Let me zoom in. Let me use this. Okay, so let's just start with this example here on the left. Here's the absolute maximum. Here's the absolute minimum. Here's the absolute minimum. In this case, it's a negative value. That's okay. Here's the absolute maximum. Notice in these cases, the absolute max and min, or like here, they're not occurring at the endpoints. They're occurring somewhere inside the domain of the function from here to here. Here is a situation where an absolute minimum is occurring at an endpoint, right? Absolute maxes and mins can occur at endpoints of the domain. It's local minima and maxima that cannot. So here, the absolute maximum is occurring at the endpoint of the domain, and here the absolute maximum is occurring not at the endpoint. In this example here, which is about as far over as I can get it, in this example, the absolute minimum value is being achieved twice. So it's being achieved, oops, here and here. And that's the absolute minimum value. Here, the absolute maximum is occurring in right there. It's only achieved once. So there's all sorts of possibilities for what can happen with these absolute or global max and mins. Okay, so take that to heart. Now, the other important point is this. If any of the two hypotheses of the extreme value theorem are not satisfied, all bets are off. The theorem may fail. Let me just remind you all, there's two hypotheses, two requirements to get the conclusion here. I'll highlight them. One requirement is F is continuous. You got to have continuity. The other requirement is this, closed interval. So if you have those two things satisfied, you're guaranteed absolute max and min. If either one of them is not true, all bets are off. All bets are off. You may not actually get an absolute minimum and an absolute maximum. So I've got some counter examples right here. So if F is not continuous, the theorem may fail. And this is an example of that, okay? So let me kind of point out what's going on with this. I'm going to zoom in here too. Yeah, so here's the domain of F. It's a closed interval, right? It's a closed interval from A to B. These are included. That is satisfied, but our function's not continuous on that interval. It's got a big gap in it, right? So to graph this function, I have to pick up the pencil. I have to go, here's one piece, oh, and then here's the next piece. Okay, so because of that break, there may not be an absolute maximum or an absolute minimum. And this is exactly a situation where that occurs. The absolute maximum value is not attained, so this function doesn't have an absolute max. Now, it's still defined on the whole interval, right? It's just at this point here, it's not defined there, but it is defined there. So it's not continuous, but it is defined on that closed interval, but not achieving an absolute maximum. Boo. Okay. Now, if the domain is not closed, but your function is still continuous, all bets are off again. So that's this example over here. Kind of show it. There we go. Here, the domain is not closed. It's not closed on this side, right? This point is included, this point is not. The function itself is continuous. I didn't have to pick up the pencil to draw that. And it keeps going, right? It's continuous, but absolute minimum value is not attained because the function keeps getting larger and larger negatively, and it never achieves an absolute minimum value. Meaning, if you gave me a potential minimum value, -1 billion, I would say, well, -1 billion and one is still achieved by the function. And then you go, okay, well, -1 billion and one is the absolute minimum. And I go, well, -1 billion and two is still achieved by the function. And then you can repeat that forever. So the absolute minimum value is never attained. Okay, this is all to say, summarize one more time, you need those two conditions to get the conclusion of the extreme value theorem. All right? Okay, so on that note, let's play. I'm always excited to do activities. I'm excited to work with you. Your instructors are excited to work with you. The tutors are excited to work with you on these. Hopefully this all makes sense. Remember, if it doesn't, you can seek out help, ask us questions. We are more than happy to help. I will stop rambling now. Thank you again, and I will see you next time for section 2.5. All right? Have a good one, everybody.